Okay, so there is a ring of charge. The radius of the ring is capital R. The distance from the center of the ring to point P is called X. We have a uniform charge distribution, so lambda would be dq over dl, where L is the length of our circle or the circumference of the ring. The electric field, due to this bit of charge, this little dq here, would be directed down and to the right there. A little electric field down there. So now we just need to substitute into our electric field equation here the appropriate values. Now, the cool thing about this problem is all of our dq is at the same distance from point P. So that's going to make some of this a lot easier to deal with. So, first of all, our net R hat is in the x direction, and so the x component would be cosine theta. If this is the angle, that would be theta, which makes this theta. So we need the x component. And the cosine of theta is what? Adjacent over hypotenuse, so would that be x over little r? And by definition, what would little r equal? Capital R squared plus x squared? Okay, so I have a substitution for r hat. I have a substitution for r, but I don't have to substitute in for dq because the dq isn't changing. It's not a different distance. So our electric field will be the integral of k dq over r squared plus x squared, all squared, times r hat, which is x over r, but r is the square root of r squared plus x squared. We're actually going to take this integral with respect to q as we go from no charge all the way around to the total charge q. X is constant, r is constant. The only thing that we're changing is we're adding up all the charges all the way around the circle. So would this be k q x over, what's that? Capital R squared plus x squared raised to the 3/2? And that would be in the right form for our unit. Looks good. Alright, so for this guy, we are going to find the electric field. And we need to sum up all the electric field lines due to all the little DQs, the little bits of charge that are smeared out over this flat disk. And there's an R hat there that represents that it's a unit vector. So, what is R hat going to be in this problem? X hat, and that would be the cosine of the angle, where this is theta, and this is theta. So if we're going to define dq, this is a charge smeared over an area. So sigma would be the charge per area, or dq dA. Alright, so dA refers to a little bit of surface area of our disk. but we can actually come up with the area of the surface of the disk, dA, by looking at it as a bunch of rings stacked on top of themselves. So we start out with a little ring and we put another one on and another one on and pretend like I can make beautiful symmetrical rings where all of those circles are perfect, and they're not. But so we would add up all of these circles, all these rings become a disk. So if I want to find a little bit of the area, because it's a little teeny bit of the area, I need to multiply length times width. The length of one of my rings would be 2 pi r. The width of one of my little rings is a little bit of the radius dr. And that would give me the surface area of this little ring. So then for dq would be sigma dA, where dA is 2 pi r dr. Now let's put all this together as best we can. So our electric field would be the integral of K. dq is going to be sigma 2 pi r dr over r squared, and r squared is the distance from, or r is the distance from dq to point P, which is going to depend on x and this distance right there. Let me change my letters here. I'm going to make you mad. Can we make this a capital R? Got to be the least destructive. Instead of the radius of our circle being capital R, let's just make it A. The radius is a little a. Or B, or C, I don't really care. Not an R. Capital R is going to be the distance from DQ to point P. So then the variable distance from the center of our disk to our little dq can be r. And then that way our capital R would be the square root of r squared plus x squared. So then down here, this would be the square root of little r squared plus x squared, all squared. So that should be r squared plus x squared. R hat is x hat, which is the cosine of theta. And the cosine of theta, let's go back up here. Cosine would be adjacent over hypotenuse. So would this be adjacent x over hypotenuse, the square root of r squared plus x squared? All under the square root. So now I have to substitute that in for the r hat slash x hat slash cosine theta. So that will be x over the square root of r squared plus x squared. So how do we take the integral of that sucker? Well, let's put some limits on here first. So we're integrating with respect to r, little r, which is the variable radius of our disk. Because remember, we are creating a disk by adding rings of R1, R2, R3, R4, R5, R6, R7, R8, all the way to R equals A. So we're going to go from 0 radius to A radius. X is a constant. K is a constant. Sigma is a constant. 2 pi is a constant. We got a lot of constants going on there. But we're integrating with respect to r. And oh my, there's an r and a x squared and all this business down here. So let me clean this up a bit. Let's pull out our, you want to pull out the constants? We'll have k lambda 2 pi x 0 to a of r dr over, would that be r squared plus x squared to the 3/2? Okay, so because this is really yucky to integrate all by itself, we can do some substitution. Let's let a new variable u be equal to r squared plus x squared. So if I take the derivative of u with respect to x, I'll have 2x dx. Okay, so then that's 2r dr. All right, so I can substitute u for this stuff right here. U to the 3/2. Okay, and now look, r dr. I can divide by 2 on both sides, and a r dr will be the same thing as du over 2. So 1 over 2 integral of du to the u, like that? I just said along u. They're going to like listening to that at 50 something seconds. Now what? Is that right? So now what? Is that good? So does that make it negative 1 over u to the 1/2? Is that good? So now the electric field, what did we factor out? We factored out a k, a sigma, a pi, a 2, and an x. And now this would be negative 1 over, what was u? R squared plus x squared. Evaluated from 0 to a. So now we evaluate. So could I write this as 1 over the square root of a squared plus x squared minus negative 1 over the square root of 0 plus x squared? So 2k sigma pi x, that would be 1 over x minus 1 over the square root of a squared plus x squared. So yay! And that is the electric field at a distance above the center of a uniformly charged disk. Hooray! Okay, so So let's do an arc of charge. Hopefully at some point you'll get to where you see how this all works and can at least set it up, even if you can't take the integral. Alright, so I'm making just a dotty dot dot coordinate system there. And that's a circle, not an arc. Let's put point P right here. So our charge smeared out over this arc. It has a radius of A. And if we have a little bit of charge right here, you're going to have an electric field, boop, pointing down and to the right. If you have a little charge over here, you're going to have an electric field pointing down and to the left. So overall, what's the direction of our electric field? It'll be straight down. Okay, so if we're going to find this electric field due to a charge distribution, we need to sum up the electric field contributions of each one of our little DQs at their specific distances with a certain direction. We need to define our little bits and pieces. What does DQ mean? Well, this is a nice bent straight line. So, what do we use for the density of charge smeared out over a line? Lambda. Lambda would be our DQ DL. Now, DL is a little bit of the arc length. DL is a little bit of the arc length. How do you find arc length? So I'm going to blow it up. So DL would be a little bit of this arc length. And you've got your radius business going on here. How would you find that little length right there? Is arc length r theta? So would a little bit of an arc length be r times a little bit of an angle change? So then our dq would be lambda r d theta. And if we're looking at this little dq right here, and there's r, and I'm looking at the angle that I have from the x-axis here, wouldn't this angle theta be that angle theta there? Vertical angle theorem business. So r is constant. R would just be A. Now what about r hat? Which direction is our electric field at in? It's in the y direction, so I'm going to replace it with y hat. And the y component would be what? Sine theta. And let's see what we get. So our electric field is the sum of k times lambda r d theta over a squared sine theta. And we're going to integrate with respect to theta. So as we're sweeping out through, what would theta be? 0 to pi? Very good. We can pull out the stuff that's constant. Our electric field would be K lambda R, but R is A, so let's fix that. I'll fix it in both places, right here and right there. Sorry, kids. What's the integral of sine theta? Alright, so we'll make our substitution. So what is the cosine of pi? Isn't that -1? So I have a negative times a -1 minus, and the cosine of 0 is 1. Right? So what do we get? 2k lambda over A?